had released energy from within the atom in the first atomic blast. We are apt to think of atomic energy as something new. But God placed this fabulous energy in every bit of matter when He created it. In fact, the earth has been warmed and lighted by atomic energy from the beginning, for the energy of the sun is atomic energy. No, atomic energy is not new. But now that man can control energy, the world is faced with problems of history. But the question arises, just what is atomic energy? Well, let's begin back at the beginning. Perhaps it can be said that the cornerstone of our knowledge in this atomic age was laid back in the year 1905, when an unknown clerk in a Swiss patent office scribbled strange equations at his desk. Here, about half a century ago, Albert Einstein gave to the world E equals mc squared. Energy, the equivalent of mass. A radically new conception, key to the atomic age. The idea expressed in E equals mc squared is actually quite simple, but it has caused a great revolution in scientific thinking. It means that any object, this desk, pencil, piece of paper, just any bit of matter represents an unbelievable amount of energy. For example, the atomic energy in, just the paper of this book is the equivalent of the power produced by Hoover Dam in 1 full year of operation, enough to supply the electrical needs of your home for 1 million years. Air is a fragile thing, yet in a single breath is energy equivalent to the burning of 200,000 gallons of high-octane gasoline, sufficient fuel to fly a giant 4-engined airliner to the moon. Within just the paper of this railroad ticket is enough energy to power a cracked diesel-electric streamliner 3 times around the world. In fact, the atomic energy in 1 pound of any kind of matter, a pint of water, for example, is the equivalent of the burning of 1.5 million tons of coal. Now, of course, this doesn't mean that you can take a pint of water and pour it in the gas tank of your family car, take off on a trip around the world, but the energy is there, hidden down inside the tiny particles of which all matter is made. In order to understand this properly, we must know something about the structure of matter. Matter may exist in any one of 3 states. The same substance may be either a solid, a liquid, or a gas, depending upon its temperature and the pressure. Water is a good example. It may be a solid, ice, or a liquid, or a gas. But even in the gaseous state, it's still H2O. What do we mean when we describe water as H2O? And what does all this have to do with atomic energy? Well, to grasp what this simple formula really means is to understand some of the basic laws governing the structure of all matter. Electrolysis apparatus will help us understand why the chemist has called water H2O. The glass tubes of the apparatus are filled with water from the reservoir above. At the base of the tubes, an electric current is caused to flow through the water from one platinum-tipped electrode to the other. Immediately, bubbles of gas form and go streaming upward. Graduated scales on the tubes indicate the proportion in which these gases are released. On one tube, we read 20. On the other, 10. The greater amount of gas burns with an almost invisible blue flame, hydrogen. The other gas causes a glowing splint to burst into flame. This is oxygen. So we say that water is composed of 2 gases, hydrogen and oxygen, combined in a proportion of 2 to 1. 2 particles called atoms of hydrogen
are combined with one atom of oxygen to form a molecule of water, H2O. Two colorless, odorless, invisible gases combine to form a liquid. Individual atoms of any substance are much too small to be seen. If we had 1,000,000 of them in a pile, we couldn't even see the pile. You might say, well, if we can't see atoms, how do we know that they exist? Well, there are a number of ways that we can detect their presence. Brownian motion is one of them. If we draw the smoke of an ordinary match into a smoke chamber and then place it on the stage of a very high-power microscope with dark field illumination, we can see something that is really quite amazing. Notice the white spot. They're smoke particles. Why are they moving? They're being buffeted about by invisible particles of air. Air pressure is merely the resultant of untold billions of these particles bombarding an object. At sea level, their combined pressure is 14 7/10 pounds per square inch. That means that on a can like this, there are some 8 tons of pressure exerted on the surface. Why doesn't it collapse? Well, that's because air molecules on the inside are exerting an equal but opposite force. Of course, the velocity of the air particles is determined by their temperature. As the temperature goes up, their speed increases. So let's heat the air inside the can. The air molecules inside the can, here mixed with water molecules, are speeding up. And so some of them are forced out of the can. This smaller number inside going faster equalize the outside pressure. But now let's turn the heat off and put the cap tightly on the can so that none of the particles we have driven out can get back inside. As the air inside cools off, these particles slow down and wage a losing battle against the greater number of particles, hammering on the outside, and the can collapses. The effects of air pressure, the movement of the smoke particles, are evidences of the existence of these invisible particles, but certainly they're not the only evidences. For the whole atomic age is built upon certain and positive knowledge of their existence. The atom is not a solid pellet of matter. Instead, it's quite like a solar system. It has a central nucleus and then electrons revolving in orbits about the nucleus. And like the solar system, it's almost entirely empty space. A moment ago, we analyzed water. We found that it was made of 2 substances, hydrogen and oxygen. This represents the hydrogen atom, the simplest of them all. It has just 1 electron revolving about its nucleus. The oxygen atom is considerably more complex. There are 8 electrons revolving about its nucleus, which itself is more complex. All of the substances in the material universe, all of the millions of different kinds of things, living and non-living, are made of just a little over 100 of these building blocks of different configuration. Hydrogen, we said, had 1 electron revolving about the nucleus. Well, if there were 2, it wouldn't be hydrogen, but helium. 3, it wouldn't be a gas at all, but instead would be lithium, a silvery white metal. And so we see that these building blocks, which the Creator has made, form all of the material substance of the universe. But in addition, they are also the source of every bit of power in the universe. All of us are familiar with chemical energy. When we light a match, it burns because chemical energy is liberated. Our civilization has been built upon chemical energy. But even with chemical energy, the atom is the ultimate source of power. Only with chemical energy, it is the electrons, the outer part of the atom, that are involved. With atomic or nuclear energy, however, it's the nucleus, the very heart of the atom. Until recently, chemical energy is all that we've known. But on that fateful morning of July 16, 1945, a new age was ushered in as man released nuclear energy for the first time. A source of power millions of times greater than anything we'd known before. Let's see if we can illustrate the difference between chemical energy and nuclear energy. A firecracker is chemical energy. When that firecracker went off, it made quite a fuss, didn't it? That was chemical energy. And you know, it's a good thing it was. If it were possible for us to release the total nuclear energy in the same firecracker, it would equal 10 million sticks of dynamite. That's the difference between chemical energy and nuclear energy. Now, how is nuclear energy released? Well, one way is to split the nucleus in two. Actually break it in half. When this is accomplished, some very strange and wonderful things happen. In the first place, the two halves, weighed together, will weigh less than the whole did before. Some of the mass has disappeared in a burst of energy. You remember our formula, E equals mc squared? The equivalence of mass and energy. To split an atom, we must fire a projectile of the right size and velocity and strike the atom in just the right place. Sounds simple, doesn't it? Actually, it's far from simple. Remember, no one has ever seen an atom. And the target is even smaller. And the atomic projectile is still smaller. To meet the requirements of this exacting task, giant instruments such as the cyclotron have been built, designed to fire a torrent of subatomic particles at the nucleus of the atom. In this model of the cyclotron, steel balls represent atomic particles which are guided in a circular path by a strong magnetic field. Under the influence of electrical forces, the stream of atomic particles spiral out faster and faster until they hit the target at the periphery. But now from the model to the instrument itself, the famous 60-inch medical cyclotron at the University of California. The material to be bombarded is coated on a plate and then carefully mounted in the target assembly. This target is then fixed to the cyclotron in such a way that the beam of high-energy particles will strike it. In the control room behind a protective barrier, the operator puts the cyclotron into operation. Radiation-absorbing lead bolts provide safe temporary storage for the irradiated targets as they await their use in the laboratories of medical research. Probing still further into the mysteries of the atom is the 184-inch cyclotron, also at the Radiation Laboratory of the University of California. This great 4,000-ton instrument spans 56 feet and towers 33 feet above its foundation, and accelerates particles to far greater energies than its 60-inch companion. We are now within the very heart of the 184-inch cyclotron, inside the tank, between the pole pieces of the great 4,000-ton magnet. During operation, this area is a vacuum, traversed by a spiraling torrent of atomic particles, accelerated to velocities approaching the speed of light. In the cyclotron and other accelerators, such as the synchrotron and the bevatron and the linear accelerator, atomic energy can be released, but only in small quantities. These are essentially research tools designed to give us more knowledge of the structure of the atom. Release of atomic energy on a large scale became possible when a method of sustaining a chain of atomic splits in an isotope of uranium was discovered. The production of the first atomic bomb was a frantic race against time. The urgency of war necessitated a whole generation of time being compressed into a hectic 5 years, and it was at a cost of $2,000 million. At the peak of the activity, almost 500,000 persons pooled their efforts under the tightest of wartime censorship. The success of the gigantic undertaking was dramatically demonstrated that morning at Alamogordo when the first white-hot nuclear fires this side of the sun lit the New Mexico hills. 3 weeks after the first experimental blast, an atomic bomb was dropped on the Japanese city of Hiroshima, and then 3 days later, another on Nagasaki. These are pictures of that actual blast that destroyed the city of Nagasaki. 2 bombs have utterly destroyed 2 cities, snuffed out the lives of 150,000 human beings, and ended a war. But still, there were many questions concerning the atomic bomb that remained unanswered. Monstrous-scale tests in the Marshall Islands were planned to provide the answers. Into Bikini Lagoon came a fleet of 90 target vessels, led by the venerable old battleship Nevada, painted a gaudy red as bullseye for the target array. Ashore, steel towers were erected to house especially designed scientific instruments and cameras of all types and sizes. Doors of reinforced concrete and lead protected film from the effects of radioactivity. Flying boats joined the huge fleet of photographic aircraft. This was the most photographed event in history. The day of the first test arrives. Observation, weather, and instrument planes take to the air from their base on a neighboring island. The atom bomb is aboard, and it's set to explode above the surface of the water. Destination, Bikini. From the weather plane, blast gauges are parachuted toward the target. Bombs away. Now for the second atomic blast, this one to be detonated underwater. Boarding the firing ship, the USS Cumberland Sound, Los Alamos engineers present their credentials to Marine Guard. Security is the watchword. Aboard this electronic control ship, signals will be transmitted to detonate the bomb. The timing laboratory is a maze of complex electronics equipment, interlocking radio transmitters, automatic timers, and recorders. Transmitters are warmed up and adjusted. Graph cards changed on time recorders. Only 2 minutes to go. The standby signal to all hands. At the central control console, Dr. Marshall Holloway, the leader of the group, throws the switch for the 30-second signal. At the automatic firing board, the last 15 seconds are broadcast.
15, 10, 5, 4, 3, 2, 1.
A terror-stricken world shifted its gaze from this coral atoll in the Pacific to a parched valley in the Nevada desert. A new and more potent principle, nuclear fusion, was demonstrated in 1952 in the Pacific as the first hydrogen bomb was detonated. This bomb caused a Pacific island 3 miles long and 1 mile wide to completely disappear. And it could do the same to a city. Power of this dimension at our fingertips, let's think for a moment about the possibilities of the future. Man has within his grasp the power to wipe out civilization and practically destroy the earth in a few days' time. But again, he has the power that can carry him into outer space. For the first time in history, his foot is on the threshold of the vast, illimitable universe. Here before us is a tremendous potential, of benefit or of destruction, of good or of evil. Who will decide which it shall be? Well, one thing is certain, science alone can't decide it. The question will be decided by the people of the world, by you and by me. And the answer will depend upon what kind of people we are. Yes, science has given us a fearful and yet a very wonderful thing to use. How it is used will be determined by things hidden deep down in the hearts of men. Nuclear power is the basic power of the universe. As we step into this awesome realm, we seem to be standing before the presence of the Creator himself. It's enormously important that we appreciate this. And that first of all, we have reverence and respect for the power of the Creator. And now, as never before, we see the importance of faith, of righteousness, and of humility before God, principles upon which this country was founded, and the only principles upon which it can continue to exist. In unleashing the power of the atom, science has set before us a tremendous challenge, and at the same time has brought to our attention
the fact that the paramount issue is the rightness of our relationship to God. And every other issue, however important it may be, becomes secondary beside it.
Medical self-help is an emergency measure to be used only in cases of sudden or extraordinary misfortune. If people require medical care in the course of normal, everyday living, they should always be treated by a doctor. However, when disaster strikes, you may not be able to obtain trained medical aid in time. There are many forms of disaster. They can happen to you and your family at any moment. This film is one of a series on medical self-help. Its purpose is to teach you what to do in an emergency situation when there is no doctor.
This powerful X-ray machine, a tool of medical science, is being used for healing purposes. The radiant energy it emits is able to kill all living tissue within its beam, both sick and healthy cells of the human body. Its invisible rays so highly penetrative that protective shielding with lead glass windows must be used. X-rays are much like the gamma rays of radioactive fallout. We began our picture with X-rays because you are all to some degree familiar with their effects. But radioactive fallout is another matter. If you're like most people, it creates many questions in your mind, and you have doubtless read or heard some falsehoods and misconceptions. This film will tell you what you need to know about fallout, so that if our country is ever subjected to a nuclear attack, you can help yourself and your family to survive its dangers. For fallout is probably the most dangerous product of nuclear disaster in terms of the number of people who could be affected. It is also the one from which we are best able to protect ourselves. Let's examine what happens when a nuclear weapon is exploded near the Earth. First, there is blast, or the pressure wave created by the explosion, along with heat, the most intense ever created on Earth. Both will extend great distances from the point of the explosion, from 1 to 20 or 25 miles, depending on the size of the weapon. However, the further away you are from the site of the explosion, the less are the chances you will suffer the fatal effects of blast and heat. There is yet a third immediate result of a nuclear detonation: initial radiation. The final effect is residual radiation, the main concern of this film, or radiation that follows the explosion and one that may remain at high altitudes for some time before falling back to Earth. What exactly is residual radiation? Our sun, like other stellar bodies of the universe, is a giant nuclear furnace burning at temperatures of millions of degrees, while emitting various types of radiation. Among these are gamma rays, shorter in wavelength than their closest neighbor, X-rays. The Earth's atmosphere prevents these radiations, dangerous to the health of man and animal, from reaching our planet. However, when a nuclear weapon is exploded, man is creating on Earth, in the splitting of atomic nuclei, his own nuclear furnace to produce the gamma and beta radiations of outer space. Let's see now just how this radiation is created. At the time of the burst, vast amounts of dirt, stone, and other debris, vaporized by the heat of the explosion, are sucked up into the rising cloud. As the mushroom cloud forms, these particles are made radioactive, for as they cool and condense, they are contaminated by residue from the bomb. These particles, when they fall back to Earth, are what we call radioactive fallout. Can you or anyone else predict with accuracy the pattern by which fallout particles will return to Earth? The answer is no, for fallout will depend on the number, size, and location of nuclear weapons exploded and the direction of upper air currents. Let's, for example, explore the fallout produced by one of these nuclear weapons. It sends its column of radioactive material up to 80,000 feet, or about 16 miles or more above the Earth. Here, the radioactive particles, beginning to drift downward, are at the mercy of upper air currents that vary from day to day. Descending at various altitudes through many different layers of air that may be moving at varying speeds and directions. Thus, winds on the surface of the Earth give little help in determining the direction or the occurrence of fallout. Meteorologists, with their special instruments, however, can appraise altitudes as well as the total distance fallout will be carried. In a nuclear attack, keep tuned to your local radio station. It will keep you posted where fallout is taking place and its approximate amounts. Though you may be able to see this dust once it reaches the Earth, you cannot see or detect the radiation it emits without the aid of radiological instruments. Nor can you taste, smell, or feel this radiation. Why is fallout so dangerous to human and animal life? Because each particle gives off radiation as if it were a tiny X-ray machine. This radiation consists mainly of gamma rays, which are extremely penetrating. Like X-rays, gamma rays are able to injure, even destroy the cells of our body if we are exposed to a sufficient dosage long enough, or if we eat or drink material contaminated by fallout particles. Exposure to gamma rays can make you sick, can even cause death. However, no matter how long one may be exposed to fallout, he does not become radioactive, nor can anyone catch radiation sickness from him like a contagious disease. In fact, this radiation cannot make anyone or anything radioactive. Now let us suppose that fallout has descended on this can. We'll let salt represent fallout dust. The particles don't go through the tin. The radiation does, but radiation is harmless to all except living materials. It has no effect on the food inside. Now, if you wipe away the fallout particles, or better still, wash them away, the food inside cannot be contaminated and is perfectly safe to eat. The same is true of all foods and liquids that have been protected by packagings or containers, even the thinnest layer of cellophane. If you don't swallow the dust, there is no ill effect. If water for washing is in short supply, canned goods that may have been exposed to fallout can be handled safely with a piece of paper towel. Use one sheet of paper to lift the can and turn it upside down. There is no dust on the bottom. Now dispose of the paper. Wipe the sides of the can with a new piece of towel. And don't forget to put the contaminated paper in a covered receptacle. Now open the clean top. There will be no harmful particles in the food itself. A sealed loaf of bread that has been exposed to fallout can be salvaged in a similar manner. Turn the loaf upside down to expose the bottom, which will be clear of dust. Then dispose of the towel. Now insert a sharp knife through the wax paper at the center of the loaf and cut upwards, making a slot 4 or 5 inches lengthwise. Insert your fingers through the slot and rip the paper slowly open. The bread can be safely removed to a clean place. Finally, dispose of the wax paper. Contaminated vegetables, such as potatoes, can be pared like this. Use a clean piece of newspaper and, working first in one corner, cut off one end. Move to a clean surface of the paper and peel in this manner. Move to another area of the paper and remove the other end. Dispose of all peelings and soiled paper carefully. After handling any contaminated food containers or vegetables, wash your hands. Fallout dust is dangerous, but it can be dealt with by following safe procedures. There is another widespread legend, the fear that fallout spells death to all life on Earth. The plain fact is that even if a great number of nuclear weapons were exploded, the resulting fallout would cover only a small area of the world's total land mass. The real concern then is this: if we are in that area, how do we protect ourselves? Like X-rays, radiation from fallout can go through almost every kind of building material. Over 99% would pass through glass, 66% through wood sheathing, 50% through a brick veneer wall. But only 1% of gamma radiation would penetrate 18 inches of concrete. And though it's not a building material, it's important to know that only 1% would pass through 25 inches of earth. Quite aside from the shielding effect of building materials, the intensity of radiation decreases with the square of the distance from the source. Thus, 10 feet away from a particle of fallout, the radiation rate is only 1% of that encountered at a distance of 1 foot. Other things being equal, the central parts of a building are safer. The radiation rate, or the intensity from fallout, decreases with the passage of time. In fact, for every 7-fold increase in time, the radiation will be reduced by a factor of 10. That means that at 7 hours after the explosion, the radiation level will be about 10% of its intensity at 1 hour. At 49 hours, it will be about 1%. Within 2 weeks, the radiation rate can be expected to decay to about 1/10 of 1%. Therefore, the most vital period to seek protection from fallout is the first few days after nuclear attack, even more so the first few hours. But remember, even with the passage of time, a low level of radiation can be dangerous. That is why you may need to remain within a sheltered area for as long as 2 weeks. These, then, are the 3 basic factors in protection against fallout: time, distance, and shielding. Time, meaning the longer you stay protected from fallout, the safer you will be. Distance, or the further away you get from fallout, the safer you will be. Shielding, meaning the more mass or weight you put between yourself and fallout, the safer you will be. You have often seen this sign on buildings. It means that indoors is a public fallout shelter, one of many and various kinds of buildings in your community that are similarly identified. Architects and engineers have carefully surveyed the shielding qualities of these areas to ensure they offer a minimum protection factor of 40 or more, meaning that in the event of fallout from a nuclear explosion, the mass and weight this shelter will place between you and the source of radiation will make you at least 40 times safer than if you were outdoors. Each of these shelters will hold at least 50 people and has been stocked by the government with austere supplies: food, water, sanitation equipment, medical kits, and radiological instruments. But what about millions who live in suburbs or rural areas, often far beyond quick walking distance of the nearest public shelter? With foresight, you can have a home shelter for the protection of your family, built from specifications and cost estimates for various types of shelters provided by your local civil defense office. The home shelter should be stocked with supplies of food and water sufficient for 2 weeks. Here you are afforded time, distance, and shielding if and when fallout so dangerous to human health should ever occur in your community. Just how much radiation can you receive without becoming sick? We measure exposure to gamma radiation from fallout in units called Roentgens. They're the same units used to measure X-rays, named for Wilhelm Conrad Roentgen, the discoverer of X-rays. People and animals may develop radiation sickness if they have been exposed to large amounts of radiation over a short period of time. Few people become sick who have been exposed to a total radiation dose of 100 Roentgens or less. However, exposure to more than 300 Roentgens over a period of a few days will cause sickness, may cause death. And if you receive an exposure of 600 Roentgens in that same period of time, death is almost certain. How can you tell just how much radiation you've been exposed to? These are the instruments commonly used to detect and measure radiation. They are part of the equipment supplied to the radiological monitoring team of every public shelter. With them, you can determine not only the total amounts of radiation received, but also the dose rate per unit of time, or the dose rate in Roentgens per hour. This is the dosimeter, conveniently shaped to be worn on one's person at all times. It is able to measure the total accumulated radiation exposure in Roentgens. The charger adjusts the dosimeter to a zero reading prior to its use, with each separate exposure to radiation building cumulatively on the dosimeter gauge so that a reading of the total dose is available at any given time. Next, the Geiger counter. This instrument measures radiation in fractions of Roentgens per hour within or outside the shelter. Finally, the survey meter, able to measure higher intensities of radiation that may exist outside the shelter. For home shelters, detection and measuring instruments are available from commercial sources. However, most householders will rely chiefly on their portable radios to receive readings as they are taken by civil defense monitoring teams. If there is a nuclear attack and you survive the initial effects of an explosion, you will have at least a half hour to get to a public or home fallout shelter. Therefore, to be safe from radiation sickness, get into the best available shelter as soon as possible. Once there, stay put, because each time you're exposed to fallout radiation over a period of a few days, the dosage continues to build until it reaches dangerous quantities. If you're among those compelled to travel through a fallout area on essential errands, there are certain rules to follow. Protect your body with boots or rubbers, gloves, headgear, and outer clothing that can be removed before you re-enter the shelter. On returning, brush off the rest of your clothing thoroughly, as well as any parts of your body that may have been exposed to fallout. If sufficient water is available, wash your face and hands carefully. Remember, these are the dosages of radiation as they affect human health. 100 Roentgens, little or no effects. 300 Roentgens, sickness or death. 600 Roentgens, death. Recovery from radiation sickness is nothing new. Patients who are treated by X-rays routinely experience this sickness and get over it. Of course, the dosages they receive are carefully measured. Just as in combating the virus of the common cold, your general state of health will often govern how quickly you can throw off the effects of mild or moderate radiation sickness. In an emergency situation where there is no doctor, always treat radiation sickness by treating its symptoms. In fact, these symptoms are often similar to those produced by extreme anxiety or emotional stress. So it's best not to try to determine their cause. I repeat, do not try to diagnose. Merely treat the symptoms, just as you would if they were the result of any other type of illness. These are the symptoms of mild as well as moderate radiation sickness, one or more of which may appear shortly after exposure to fallout. Fatigue, loss of appetite, nausea, vomiting, prostration. The treatment is rest. For nausea, you may give the patient any of the commercial preparations that settle an upset stomach, or 1/2 teaspoon of baking soda in a cup of water. Tea and other hot liquids may be helpful. When a high fever is present, apply cold wet packs. Aspirin also tends to reduce a fever. In severe radiation sickness, along with the early symptoms, other symptoms may appear a week or more after exposure. Recovery is possible, but it'll take longer. The symptoms are diarrhea, inflammation of mouth and throat, loss of hair. For treatment, control the diarrhea and give aspirin and warm water gargles. People are naturally alarmed at the thought of bodily changes that may follow severe radiation sickness, such as loss of hair or sterility. These conditions are usually temporary and will disappear with recovery. So I hope we've dispelled another commonly held myth. You can get over radiation sickness just as you get over many others. Nevertheless, don't minimize the danger of fallout. Remember, its effects are cumulative. The only real protection against it is to take shelter. Now, let's review some of the outstanding facts we have learned in this brief exploration of a vitally important subject. Fallout is composed of trillions of particles of dust that are made radioactive by residue from the nuclear weapon during the aftermath of the explosion. In a nuclear attack, depend on your local radio station to tell you where fallout is taking place. You may be able to see some of the fallout dust when it reaches the earth, but you cannot taste, smell, or feel the radiation itself. The gamma rays given off by fallout are able to injure or destroy the living cells of our body if we are exposed long enough. Food or water in containers that prevent contamination by fallout dust is perfectly safe. Radiation is harmful only to living tissues. Packaged foods that have been exposed to fallout should be opened carefully. By following proper procedures, you can eat such foods without danger to health. Radiation can pass through most building materials, but its intensity is diminished in proportion to the weight and mass of the material or the shielding. The intensity also decreases with distance from the fallout. The radiation rate will decrease or decay rapidly with time. It is most dangerous in the first few days after explosion. Thus, the three basic factors that protect you from fallout radiation are time, distance, and shielding. You should know the location of the nearest public shelter in your community. Inside it, you will be at least 40 times safer from fallout than you would be outdoors. And it has been stocked with supplies to sustain its occupants for up to 2 weeks. If you're not within walking distance of a public shelter, you can provide a satisfactory home shelter for your family. Radiation is invisible, but we have accurate instruments with which to measure it in Roentgen units. The dosimeter can be worn on the person and measures the accumulated radiation exposure, the total dose at any given time. The Geiger counter measures radiation in fractions of Roentgens per hour, inside or outside the shelter. The survey meter is used to measure the higher intensities of radiation that may be present outside the shelter. Assuming that you have the protection of a good shelter within a half hour after nuclear attack, you will probably have little or no radiation sickness. If there are victims who appear to have radiation sickness, do not diagnose. Treat the symptoms. Perhaps the most important thing you have learned is to see the danger in its true perspective. Make no mistake, nuclear attack would be a terrible catastrophe. Millions of our people would be killed by the initial blast and heat. Millions more would be threatened by death from radioactive fallout. But that is a threat that can be combated. Can, with knowledge, preparation, and courage, be faced and conquered.
July 16th, 1945. This is the darkness of a desert morning. And here in New Mexico, a group of men wait tensely, expectantly. Behind them, 3 unbroken years of work. Work done in unprecedented secrecy. Recorded from 6 miles away, these views of the most concentrated release of explosive energy in the history of mankind. From the time of that first explosion until Hiroshima shuddered beneath the release of atomic energy, work on the bomb went steadily forward in closely guarded plants in New Mexico, Oak Ridge, Tennessee, and Hanford, Washington. For over 100 years, the city of Hiroshima had garrisoned some of the Japanese Empire's finest troops. The city had never been subjected to actual bombing, but had been warned repeatedly. Now its army headquarters, barracks, ordnance and quartermaster depots, factories, mills, and shipyards were to feel the weight of the atom's destructive power. 21 days after the New Mexico experiment, a B-29 was over Hiroshima carrying an atomic bomb. At 8:15 in the morning of August 6th, Japanese time, the first atomic bomb struck an enemy target. This is 0 Point on Hiroshima, the exact spot above the city at which the bomb burst over enemy territory, at the junction of the Matoyusu and Oto rivers. The atomic bomb was intentionally exploded well above its target in order to dissipate its radioactive material. The devastation you see here was caused by the explosion of the bomb above this 0 Point. Only the strongest buildings are left standing, and they are gutted. Looking north from 0 Point, this is what was left. Looking east, the camera records a scene of complete devastation in the immediate area. To the south, these are the ruins. Looking west from 0 Point, the same complete leveling is evident, the same inability of structures to withstand atomic power. Just 1/10 of a mile from 0 Point, the effect of the bomb blast can be seen on these stripped and broken trees and on this Russian-Japanese war memorial. Lines were literally blasted into the stone of the memorial. Here, looking west from the Sanwa building, the side of a concrete smokestack nearest the blast has been discolored. The Hiroshima Gas Company building on the right in this picture has been almost completely demolished by the force of the explosion from above, as though struck by a giant sledgehammer. The reinforced concrete Sanwa Bank building was wrecked even more completely. These twisted steel beams once supported the roof. The direction of the bomb blast can be seen clearly in these scenes of the concrete parapet wall extending above the bank building's roof. Two-tenths of a mile from 0 Point was a Shinto shrine. Here, too, the blast stripped the trees and collapsed stonework. Originally, the base of this statue was polished granite, but now the stone is roughened by the force of the blast, which completely removed the polish. The lighter surfaces which are being pointed out indicate the angle of the bomb blast as though painted on the surface. The nearby lamppost shows flash burns on the side facing the blast. The Commercial Museum was also within 2/10 of a mile of 0 Point, and the garden wall facing the blast was bent inward by the push of the explosion. The downward force of the blast caused the failure of the concrete beams which supported this roof, and the roof itself has settled so much that it now acts as a reservoir. Looking east, an area of complete devastation is all that can be seen. The railing was blown off this bridge, and the steel poles on the bridge show the effects of the atomic bomb blast, which hurled grit with such force as to etch the steel. The front of this school is a 1/4 of a mile from and faces 0 Point. The sag in the concrete reinforced floor can be seen here in the entrance. The steel rods, which are now hanging, once supported a suspended ceiling. This reinforced concrete building was knocked sidewise, causing the lower story to collapse. This barren area, 3/10 of a mile from 0 Point, once contained the main Japanese military headquarters. The barracks were utterly destroyed. Most of the military personnel, of approximately 20,000, were wiped out. The distorted steel framework is all that remains of a building which stood 4/10 of a mile from 0 Point. Whereas this reinforced concrete building of the Chukkogi Electric Company, 1/2 mile from 0 Point, withstood the blast much better. 6/10 of a mile out, destruction was almost as complete as it was at 0 Point. Wooden structures were completely collapsed by the blast. This was Hiroshima Castle. Its framework was demolished by the force of the blast, but fires of secondary origin did not occur. Because it happened to be at a 45-degree angle to the direction of the blast, the Hiroshima City Hall, with its heavily reinforced concrete construction, shows much less damage. Doors and windows were blown in by the force of the explosion. Shadows of the posts on Yorozuyo Bridge indicate the direction of the explosion. 6/10 of a mile from 0 Point, the bridge floor is etched except where shielded by the railing. Outlined in the surface of the bridge is the shadow of a pedestrian, which tells its own meaningful story. One mile from 0 Point, the blast damage shows lessening force, but the results of fires of secondary origin are still severe. On this side of a steel bridge over the Ota River, 1 mile away from and facing 0 Point, the lead paint was almost completely removed by the sandblast effect resulting from the explosion of the atomic bomb. The surface of the other side of the same bridge, however, was not visibly affected. Also a mile away from 0 Point is a Red Cross hospital, which, although damaged, never ceased functioning. This is the front of the building, which faces northeast. On the northwest side of the building, the steel windows and all floors were blown in. This southwest side of the building again shows windows blown in by the external air pressure caused by the explosion. Here, however, the windows in the southeast wall were blown out rather than in. A look inside the hospital shows chairs in the same position as at the time of the blast. The backs of the chairs, which faced 0 Point, were flash burned through the window. The mohair upholstery fabric was singed down to the base of the nap. The effect on this wall, which faced 0 Point, was almost identical with the damage done by the explosion to the opposite wall. In addition, interior partitions were knocked down. Looking toward 0 Point from the roof of the Red Cross Hospital a mile away, the tremendous destruction created by the first atomic bomb can be seen. Army vehicles of our occupying forces are moving through the city streets. Here, looking in the opposite direction toward the south, away from 0 Point, only a few masonry foundation walls remain, and what is left of one reinforced concrete building. Looking west, still a mile from 0 Point, the only sign of a small industrial plant is a lone concrete smokestack. Temporary housing facilities built with scrap material have been thrown up in the area. No matter what kind of construction the Japanese used, whether it consisted of wooden frame and mud plaster walls as here, or wooden lath and plaster veneer construction, they made no attempt to zone their various types of buildings. Barracks, homes, industrial centers of steel and reinforced concrete, factory buildings of brick construction, All were crowded together with no apparent regard for the safety of the civilian population. Within an area of 1 mile to 1.5 miles, there was almost complete destruction except for some reinforced concrete buildings. From 1.5 to 2 miles, there was severe damage by fire and moderate damage by blast. From 2 to 6 miles, there was minor damage by blast and fire, varying from damaged roofs to broken windows. These wooden buildings, 1.5 miles from the center of the blast, were all subject to fires of secondary origin. The Higaski Railroad Station in East Hiroshima, 1.5 miles from 0 point, although still in use, was extensively damaged. The marquee crumbled from the force of the blast and has been removed. When the marquee fell, it pulled the brick veneer off part of the building. Inside of the station, steel beams supporting the roof were twisted out of shape, and the concrete walls, though still standing, show the effects of the tremendous concussion. This high school building, the same distance from 0 point as the railroad station, had its north wall smashed in by the blast. The second story of the north wall was especially badly damaged. Looking through a bombed-out section of the wall to 0 point, notice that not all the buildings in this area were as severely damaged as the schoolhouse. A portion of the wall of the school was blown in across the desks, and partitions were shifted. The high school wall farthest from the 0 point now bulges in the direction of the blast, and all glass was blown out of the window frame. Between 0 point and the main building of the novitiate of Jesuits 4 miles away was a hill which served to lessen the intensity of the blast. Yet, despite this protection, all the windows were shattered and part of the wall blown in. The chapel, which is the left wing of the building, is built of timber with plaster walls. The glass in the doors of the main entrance foyer were shattered, and the paneled ceiling was blown loose by the force of the explosion occurring 4 miles away. A group of Jesuits who were teaching in Hiroshima witnessed and survived the explosion. One of them has provided an eyewitness account.
Father, would you introduce yourself, please?
I am Father John Zemus, professor of philosophy at the Catholic University of Tokyo, which is under management of the Jesuit fathers.
What were you doing in Hiroshima at the time of the explosion?
Well, my philosophical class was evacuated from Tokyo to Hiroshima about 5 months ago, and I was staying with my class at a house of studies at the outskirts of the city of Hiroshima.
Could you describe exactly what happened in the morning of August the 6th?
I was in my room, which faces the valley, and suddenly I saw a light, like magnesium light, flashlight, which filled the whole valley. And looking out of my window to find out the reason for this peculiar phenomena, I saw nothing besides this light, and turning from the window to the door of my room, I heard a crash. It may have been 10 seconds after seeing the light, the flashlight, and immediately I was covered with splinters of the window frames and glass sticking into the walls and actually my flesh itself. I tried to get out of my room, but found that our house had been severely damaged by the blast of this explosion. I had the impression at that time that the bomb had immediately crashed on the house. So severe, so strong was the effect of the concussion. But looking outside the house, I saw no trace of the bomb itself, but About a kilometer away from our houses, I saw several peasant houses which were on fire. After a while, we saw a procession of people coming from the outskirts of the city up the valley. Many of them, most of them, were wounded, especially the parts of the body which were not covered by clothes, like hands, feet, back. They came up to our house, and we did what we could, but there were no possibility to give much of aid. As a matter of fact, we used all our grease we had at that wartime in the house, and it was exhausted in a moment.
How many people do you think were killed?
All of us who lived through this experience at the spot estimate the numbers of deaths at least as 100,000. This estimate is not based on official figures, but just on a knowledge of special groups in under the population.
Was there anybody to take charge of the city after the disaster?
There was nobody to take charge after the disaster because all important people were practically killed. The major, the commander of the city, many high-ranking officers, a Korean prince which was stationed at the time in Hiroshima, and also the regiments of the city were wiped out.
What is your opinion as to the story that the ruins of the city emitted deadly rain?
Well, I think that it's just a rumor. Because I myself and others of us have worked in the city itself immediately after the explosion for several hours, and we felt no ill effect at all.
Tell me a little about the Japanese reaction towards the Americans and towards the atomic bomb.
Neither myself nor anybody of our fathers heard a single outburst of hate against the Americans in those terrible days. And during the whole war, we didn't experience much about hatred against the Allies. As a matter of fact, at the beginning of the war, after the big Japanese victories, the Japanese were inclined to look down on the enemy. But then, after the offensive went off according to schedule, they began to admire the skill of the Americans. And especially since the majestic B-29 appeared over Tokyo, practically every Japanese admired the technical skill of the Americans.
Father, what is your and your colleagues' opinion as to the use of the atomic bomb?
We have discussed among ourselves the ethics of the use of the bomb. Some consider it in the same category as poison gas and were against its use on the civilian population. Others were of the view that in total war, as carried on in Japan, there was no difference between civilians and soldiers, and that the bomb itself was an effective force tending to end the bloodshed, warning Japan to surrender and thus to avoid total destruction. It seems logical to me that he who supports total war in principle cannot complain of a war against civilians. The crux of the matter is whether total war in its present form is justifiable even when it serves a just purpose. Does it not have material and spiritual evil as its consequences which far exceed whatever the good that might result? When will our moralists give us a clear answer to this question?
The business of living goes on in the devastated areas of Hiroshima. In the northeastern section of the city, temporary homes are constructed of whatever materials can be salvaged from the ruins. Near the Higashi Railroad Station in eastern Hiroshima, scrap lumber, tin, and roof tile are all used in an attempt to build anew, in no matter how flimsy a fashion. Immediately following the bombing of Hiroshima, the President of the United States delivered an ultimatum to the Japanese government. Surrender or face complete destruction. The ultimatum was ignored. At 10:58 the morning of August 9th, Japanese time, the second atomic bomb was exploded over the industrial seaport city of Nagasaki. Almost the entire population of 230,000 people was engaged in the manufacture of arms, munitions, and other war products. Two great Mitsubishi factories were located in the heart of the city. To the north, one of the world's largest torpedo plants, and further south, the huge steel and arms works. The bomb, which was dropped on Nagasaki, was aimed at a point midway between the two plants in order to cause the greatest possible industrial damage. Unlike Hiroshima, the force of the explosion at Nagasaki was largely confined to the industrial valley, which was surrounded by a series of hills that shielded many other areas of the city. A great towering mushroom effect could be seen going higher and higher and reaching into the stratosphere. Because the bomb was exploded high above the ground, the greatest part of its harmful radioactive material was dissipated in the stratosphere. As a result, the area under the explosion was relatively free from radioactivity. Persons entering Nagasaki shortly after the explosion to do rescue work sustained no ill effect or injury. Of a little more than 3 square miles, there was very severe damage by blast and fire. Most buildings were reduced to rubble. Still recognizable from the air are the skeleton remainders of the Mitsubishi plants, the large steel and arms works, and the ordnance factory devoted to the manufacture of torpedoes. The Mitsubishi Steel and Arms Works extended almost a mile in length. Its buildings were modern and typical of American industrial construction, having steel frames and roof and siding of corrugated metal or asbestos. Buildings of reinforced concrete still stand amid the wreckage of steel frames. Some smokestacks survived. They offered comparatively little resistance to the blast. But as in Hiroshima, the directional force bent steel and stripped corrugated metal from the framework of the building. Where corrugated metal remained, it was pushed in like tissue paper. These buildings show a varying degree of destruction depending upon proximity to 0 point and building strength. This foundry, 3/10 of a mile away from 0 point, shows considerable damage in spite of fairly good construction. Other buildings were stronger, some being constructed to support heavy overhead cranes. Damage to equipment inside was nevertheless serious. This machinery had been used in the manufacture of naval rifles, anti-aircraft guns, and heavy artillery. In the valley, homes were scattered through factory areas. On machinery in many of these homes, piecework was carried on to help the Japanese war effort. Blast and secondary fire destroyed the lightly constructed buildings, in many cases leaving damaged equipment. Photographed from 0 point, this area of 3 1/10 square miles shows almost utter devastation by blast and fire. Note how hills in the south interrupted the blast. In the second area of 5 1/2 square miles, there was moderate damage from blast and severe damage from fires. The total area of damage covered almost 42 1/2 square miles. ranging from complete destruction to damaged roofs and broken windows. The greatest distance at which damage was measured was 12 miles, where, through a peculiar focusing of concussion, workers' barracks were knocked down. One-half mile from 0 point, a cracked smokestack. A prison of concrete and masonry 2/10 of a mile from 0 point was almost totally destroyed. The walls left standing were parallel to the direction of the blast. This area was completely wiped out from 0 point up to the church at the foot of the hills about a mile away. In the bed of the creek rests the dome, which was blown from its place at the top of the church. The gasworks was blown into a mass of twisted steel. 2 concrete walls, the remains of 2 factory buildings. Bridges showed greater destruction in Nagasaki than in Hiroshima. But even close to 0 point, the downward force of the blast failed to damage roads and railroads due to the height at which the bomb was detonated. The main north-south street of Nagasaki was in use shortly after the disaster occurred. A typical residence on the outskirts of Nagasaki, a mile and a half from 0 point. 6 weeks after the explosion of the atomic bomb over Nagasaki, the survivors are busy working at the restoration of their homes. This is the record. Endless man-hours of work. 2 B-29s, 2 atomic bombs 3 days apart, 2 cities. The tabulation of that record speaks for itself.
Attacks us with nuclear weapons, danger will come not just from blast or heat or nearby radiation effect, but also from fallout. Fallout which may occur miles and miles away from the blast. You need to know about fallout, what it is, how to detect it, and what to do to protect yourself against it. Everybody needs to know. Yes, this does mean you. Watch and listen. One day, these facts may save your life. What is this fallout, anyhow? Just bits of radioactive fall out of the mushroom cloud of the nuclear explosion and settle on the ground. These bits of matter can be dangerous. You're exposed to some radiation every day, from cosmic rays or other natural sources of radiation. These exposures are too small to hurt you. But when a wartime nuclear explosion occurs, a serious fallout follows. Thousands of tons of atomized earth, building materials, rocks, and gases may be thrown into the air. And the mushroom cloud containing them sometimes moves as high as 100,000 feet. nearly 20 miles up. Some of the radioactive particles spill out near the explosion site. Others may be carried for 10, 50, 100 miles or more. But how will you know if there is fallout? You can't hear, smell, taste, or see the radiation. But you yourself can detect the fallout particles that produce it. The easiest time to do this, without special instruments, is when the fallout is settling through the air. This starts any time from about 1/2 hour to several hours after the explosion, depending on how far away you are. And it continues to fall for an hour or longer. Usually, you can see the fallout. So if there has been an explosion of a nuclear weapon within a few hundred miles of you, you should suspect every unusual concentration of dust in the air of being fallout. After an explosion in daylight, watch any unusual accumulation of dust. At night, put a white or light-colored plate outside. Examine it every 15 minutes or so. If dust has accumulated on the plate, treat it as fallout. The particles in that fallout behave like miniature X-ray machines, sending out radiation in all directions. If there are many particles, and if you are exposed to them long enough, you will be hurt. Others will be watching for that fallout, of course. Experts will estimate the probable path and speed of approaching fallout and try to keep you posted. But it may come before you hear any details by radio or otherwise. You must take precautions, whether you hear their reports or not. If radio stations are operating, you will hear reports, especially on the Conelrad frequencies 640 or 1240 on your AM dial. As soon as it is safe for specially protected crews to get out into the open, these highly trained civil defense radiation detection teams will make a thorough check of radiation levels and characteristics. Those facts will be relayed to you by radio as fast as they come into civil defense headquarters in your area. Information from the radiation monitoring teams will be combined and analyzed by experts manning a central radiation control point. These experts, who know just how fast harmful radiation reduces in force, can predict when it will be safe for people to come out of shelters and resume normal tasks. We have warned that you may have to act before you get any detailed reports. Just what can you do if fallout comes your way? Find the best shelter you can. The more solid substance you can put between yourself and the fallout, the better. But an ordinary frame house with windows closed will give considerable protection. In a house, it's best to get on the floor, away from doors and windows. Or if you can, find a location with additional walls in the center of the building. A basement is even better if the house has one. Large buildings, such as apartment or office buildings, give good protection. The thick, heavy masonry of their walls and floors makes it hard for radiation to get through. Basements, inside rooms, or corridors on the lower floors are safest. The basement of any house or building will become a good improvised shelter if you block the windows with sandbags and place other sandbags on the floor above the shelter area. If you don't have sandbags, thick, solid layers of books, magazines or newspapers, or even a series of file cabinets standing close to each other can cut the radiation danger. In some parts of the country, there are storm cellars or outside vegetable storage cellars. They may be used as shelters from fallout. If you plan to use such a cellar or your basement or any other shelter, stock it with food and supplies. To equip and supply your shelter area, you need some of the same things you might take on a vacation camping trip. First, sleeping equipment to fit your shelter area. Folding cots, or sleeping bags and blankets. Then, food and water. There should be at least a 2-week supply. You'll want plenty of fruit juices and lots of your family's favorite canned foods. The drinking water supply should be rotated often to be sure it's fresh. And don't forget such basic needs as sugar, salt, pepper, and other seasoning that your family ordinarily uses. Now, some equipment. A radio is very important. It should be a battery portable with spare batteries. A transistorized radio is best, as the batteries last longer. Next, you need light in the form of flashlights and a battery-operated lantern. Then, a good first aid kit. Now, plates, cups, silverware. A can opener and a bottle opener are important. Add to these things enough closed containers to take care of garbage and human waste. Especially if there will be children in the shelter, include some books and magazines, paper and pencils, maybe 1 or 2 small, simple games. The best protection of all is the special shelter built according to specifications of your local civil defense organization. This has an air filter to allow ventilation, but keep dust out. And it has at least 3 feet of earth over it. It would be a good idea to go right now to your local civil defense office to secure plans for the type of shelter you want, and then to get busy on construction. Plans are simple, using standard materials. So maybe you can do the job yourself. But all this special shelter talk won't help very much if you are caught way out on the open road. If that happens, keep driving until you see a building, which may be a house or barn, church or school. Drive as close to the building as you can. Then get yourself and your family out of the car and take cover in the building. If you live on a farm and have sufficient warning, get your animals under cover and give them enough food and water to last several days. And if you can, cover any piles of hay or harvested crops that may be outside. If the explosion has been some miles away, you will have time to fill tubs and other containers with water before fallout arrives. All locations where outside dust does not penetrate will be safe storage points for water. Whatever kind of shelter you find, settle down and make the best of it. If there are others with you, help them by being as calm as you can, and don't be discouraged. You can go out for very brief periods if you are well covered and keep the dust off your skin. Wear heavy boots or shoes and pants tucked in or tied around the bottom to keep dust out. If any dust gets on you, brush it off promptly. And when you have a chance, wash it off. That dust can burn your skin. But what happens if you do get exposed to a great deal of fallout? Food or water has been contaminated by the dust, internal damage may occur. When dust has been left on skin, there will be skin burns. When you have been near dust too long, there may be radiation sickness. Exposure can even cause death. If you have had considerable exposure, you will vomit and grow weak. But after a few hours, this sensation will pass, and by the next day, you may have had the last of it. Even if you have been exposed to excessive fallout, you may eat and drink just as you normally would. But don't force yourself. Whether you have had these symptoms or not, if civil defense radio announcements have said that radiation has been high in your section, Keep an eye on your condition for the next few days. Watch especially for these developments in the 2 weeks following exposure. Return of nausea, sore throat, bruise spots developing without any known reason, loss of hair. These conditions, or nosebleed, or diarrhea, should be reported to a doctor or to the nearest first aid station set up under civil defense plans. Unless civil defense teams have warned that your area is still dangerously radioactive, you can get out and work to help yourself and help others. Although fallout can be deadly, your chances of avoiding damage from it are much better if you follow the directions we have given you. During an alert, keep your portable radio tuned to the Conelrad radio frequencies, 640 and 1240 on the AM dial, for the latest reports and advice. Right now, today, before there is an alert, take time to learn the Civil Defense 5 steps to safety. Learn warning signals and what they mean. Learn your community plan for emergency action. Learn protection from radioactive fallout. Learn first aid and home emergency preparedness steps. And learn how to use Conelrad, 640 or 1240 on the AM dial for official directions.
More than 2,000 times during World War II, torpedoes found their targets in enemy vessels as the submarine fleet of the United States Navy established a mark unequaled in the history of naval warfare. The American submarine, which saw action in World War II, is as superior to our Navy's first practical submarine as the battleship Missouri is superior to her famous ancestor, the Constitution. Our first carrier, the Langley, which was a major achievement only 30 years ago, was just a crude forerunner of today's attack carrier with her brood of jet fighter planes. Back of each and all of these advances in our Navy's striking forces, there is a story of cooperation. For the men who sail the 7 seas have long found powerful allies in those who sail the 8th sea, the vast and never fully charted ocean of scientific research. The atom bomb, spreading its mushroom cloud over Bikini Atoll in 1946, gave scientists and fighting men the opportunity to learn about the most destructive force yet devised by man and its effect on naval strategy of the future. But a bomb is atomic energy uncontrolled after its release. And men of science knew that the same energy kept under control might serve the Navy in a vastly different way. The means of obtaining that control was the reactor pile, the furnace of atomic energy. Here, the rare elements which produce nuclear fission in chain reaction, uranium-235 or plutonium, strategically placed, will release tremendous energy in the form of heat. In fact, at work in a reactor, a single pound of U-235 will provide as much heat energy as 2.5 million pounds of coal, or nearly 250,000 gallons of diesel fuel oil. And what is more, oil to burn requires oxygen. So does coal. But in the process of nuclear fission, no oxygen is required. To the men of the Navy, the new power source had limitless possibilities. None more immediately useful, perhaps, than in a submarine. A conventional sub using diesel-electric power attains its maximum range and speed on the surface. Later models, which use a snorkel or breathing tube to supply air for the diesels, achieve comparable range and speed just below the surface. But a fully submerged sub, despite tremendous improvements in batteries, which must then supply its power source, still can't maintain the speed or equal the range of either the snorkel sub or the surface sub. What's more, a sub on the surface is a comparatively easy target for the powerful electronic eyes and ears of an enemy. A snorkel sub is only relatively safer, while a fully submerged sub is safest of all from detection. But since it must surface eventually to recharge batteries, a patient enemy may still find his target. On the other hand, a submarine using atomic power with an air supply for crew could run submerged for weeks if necessary. As to speed and range, it was evident that an atomic sub should be able to cross the broadest ocean fully submerged faster than many ocean liners, and in the process use less than a pound of atomic fuel. The principle was clear. Let a nuclear reactor supply heat. Transfer that heat to boilers where water becomes steam to turn turbines, and let the turbines, through reduction gears, turn the propellers to drive the ship faster and farther than ever before. In theory, then, the atomic submarine was sound, but the problems involved in building one were staggering. The reactor itself. Of what material could it be built that would permit chain reaction while operating at the many different angles of submarine action and yet be able to survive combat shocks? How to transfer the heat from reactor to boiler? What liquid could withstand the great changes of temperature and still not act as a damper of the atomic fires? The pumping system. How to force the hot liquid from the reactor into the boiler and back to the reactor? Shielding. What substance would be light enough yet provide sure protection to the crew from the deadly rays nuclear fission produces? And finally, how to reduce the overall size of this normally bulky, complicated machinery and make room for it within a submarine, already the most compactly designed warship afloat. To answer these and the literally thousands of other questions involved, the Navy and the AEC authorized 2 separate submarine projects. Under these parallel projects, divergent but equally promising avenues of engineering and design were explored independently. Thus, the stage was set for the world's first atomic submarines, the Nautilus and the Seawolf. Much of the work on the atomic power plant for the Nautilus was carried out at the National Reactor Test Center near Arco, Idaho. Here in the empty desert wasteland, a full-size duplicate of the Nautilus engine was constructed and tested. In January 1954, the hull of the London yard of General Dynamic Company's Electric Boat Division, the organization charged with hull construction for both atomic subs. Meanwhile, development of the parallel Seawolf project has gone forward for many months, principally in Schenectady, New York, under the direction of the distinguished staff of General Electric scientists and engineers at CAPL, the Knowles Atomic Power Laboratory. Within these walls, under conditions of strict security, literally hundreds of highly trained scientists have been working with formulas that would have been meaningless a score of years ago, using techniques and, in many cases, tools which were inconceivable before the achievement of nuclear fission. This control room may bear little physical resemblance to the engine room of the finished Seawolf, yet behind its concrete walls is a full-sized reactor of the type which will drive that sub. And here, this has happened thousands of times. The chain reaction of nuclear fission has been started and stopped in the course of innumerable tests to determine the material and design of the Seawolf's atomic engine. In the Radioactive Materials Handling Laboratory, much new and necessary knowledge has been achieved in the handling of substances made hot with radioactivity. Mechanical hands daily perform tasks no human being could do directly and live. A section of metal designed for use in a vital part of the submarine engine has been made highly radioactive and is tested in a concrete-lined vault where the eyes and hands performing the operation are a dozen feet away. The test determines how much radiation this machine part has absorbed and with what effect. Hundreds of other tests have determined how to prevent any structural failures that might have endangered the underseas operation of the finished sub. In every section of the Atomic Power Lab, all its workers, from the senior craftsmen in the machine shop adapting old skills to new needs, to the youngest graduates from the nation's leading technical colleges, on to the top-ranking nuclear scientists, engineers, and management, all have been working with the Navy and AEC toward a single goal: the design and construction of an atomic engine that is at once efficient, tremendously powerful, and safe. To this end of ultimate safety, extensive land-based tests were planned for the Seawolf's engines before their installation in the actual ship. In a peaceful valley far from the sea near Schenectady, the structure for the tests was built. A steel sphere 10 times larger than man has ever built before. To form the giant ball, more than 600 plates of inch-thick steel, perfectly preformed, had to be fitted with absolute precision. An elaborate X-ray system checked the perfect seal of every inch of the thousands of feet of welding involved. While careful scientists were sure that tests conducted within the sphere would involve no leakage of radioactive gases, the steel sphere structure has provided an added precaution, a kind of super safety valve. And even as the sphere was being built, a full-scale operating model of the engine and reactor room sections of the Seawolf was under construction. As both sphere and hull were completed, there came the important day towards which so many workers of so many crafts had worked so long. What might be called a scientific launching into a scientific sea, as the hull section was moved into the sphere and operational tests were begun. While reasons of national security must conceal details of the tests within that sphere, one thing is certain. Much will be learned here of the workings of atomic engines, not only for submarines, but for many peacetime uses as well. For passenger and merchant ships, for land transportation, for electric power plants, even perhaps for the huge airplanes of the future. Meanwhile, the atomic submarines progress from drawing board to the reality of ships at sea, newest bulwarks of our national defense, powerful symbols of continuing cooperation between our scientists, our engineers, and our men of the sea, working together in atomic engineering, as in every phase of defense operations, they will continue to increase the striking force of the most powerful Navy in the world.